How do low-energy nuclear reactions, LENR, factor into cold fusion? Imagine a world where nuclear reactions happen not in the blazing heat of stars or nuclear reactors, but at room temperature. That's the intriguing idea behind cold fusion and low-energy nuclear reactions. Cold fusion is the claim that atomic nuclei can fuse together at or near room temperature, which is a huge departure from what we know about nuclear physics. Usually, fusion requires temperatures in the millions of degrees to overcome the Coulomb barrier, the force that keeps positively charged nuclei apart. But some scientists believe there might be a way around this barrier through low-energy nuclear reactions, or LENR. The story starts back in 1989 when two electrochemists, Martin Fleischmann and Stanley Pons, announced they had achieved fusion in a simple lab setup. They used heavy water and a palladium electrode and claimed to produce more heat than could be explained by normal chemical reactions. They also reported tiny traces of nuclear byproducts like neutrons and tritium, which are signs of nuclear activity. The scientific community was excited but also skeptical because their results couldn't be reliably reproduced. Still, the idea stuck around, sparking decades of curiosity and experiments. Now, LENR is a broader term that includes cold fusion but isn't limited to it. It refers to any nuclear process that occurs at low energy levels, not the extreme heat and pressure of stars or bombs. According to standard physics, nuclei should never fuse at room temperature because of the Coulomb barrier. But LENR suggests there might be a secret pathway, a kind of backdoor, that allows nuclei to get close enough to fuse without the need for intense heat. So how do LENR and cold fusion connect? Cold fusion is a specific example of LENR, focusing on the fusion of deuterium, a heavy form of hydrogen, at room temperature. If successful, it could release large amounts of energy with no radioactive waste. But LENR also covers other strange nuclear effects that might not be fusion at all. Some theories propose that neutrons, electrons, or even unknown particles act as catalysts, helping nuclear reactions happen under mild conditions. Others suggest that tiny cracks in metal lattices or resonance effects could bring nuclei close enough to fuse. Some researchers even think electron multiplication might play a role. Experiments in this field are often quirky. Sometimes they produce heat, sometimes they don't. Results can vary wildly depending on the metal used, how it's prepared, or even the history of the sample. There are stories of experiments that mysteriously generate heat for days or cause equipment to get damaged, hinting at energetic reactions. But many times, nothing unusual happens, leaving scientists puzzled. If LENR or cold fusion turns out to be real and controllable, it could revolutionize energy production. Imagine clean, limitless power without radioactive waste. That's the dream. But so far, no one has built a device that produces more energy than it consumes consistently. The mainstream scientific community remains cautious, but a small group of researchers keeps testing new ideas and refining their setups. In the end, LENR is like a big, strange umbrella that covers cold fusion and other mysterious nuclear effects. Both challenge our understanding of physics by claiming nuclear reactions can happen at everyday temperatures. The experiments are often inconsistent, and the theories are still speculative. Whether it's a real phenomenon or just experimental quirks, it's a fascinating corner of science that keeps the curiosity alive about the hidden forces and energies in our universe.